Yes, I know I'm using computer audio. Thank you. Somebody's coming in remotely. Let's see here. All righty. Come on, open up. Oh, are you opening? Probably going to end up with 6 copies of PowerPoint open up here. Come on. Let's try a test. Oh, there we go. All right, we finally get to have a lecture here today. Excellent. Good morning. Hey, guys. Okay. So, first, before I get started on this, are there any questions? By the way, if I'm sitting here, can you see the screen? You got it there? Okay. Are there any questions about HERC or the quiz that you guys are working on? Yeah? Not yet. Okay. Well, don't wait till the last minute. And remember, I can always be emailed for questions, and don't forget to use the discussion board. By the way, those of you who've been using the discussion board, it's been looking pretty good. Appreciate that. And so theoretically, oh, well, there we go. Okay, let's talk a little bit about mailboxes. And in general, it's a mechanism to provide a single value from one task to another, or from one event to a task. And the mechanism in most operating systems is generally that a mailbox will hold a pointer. And if you do mailboxes as pointers, it makes handling a mailbox pretty easy, because if it's non-zero, you've got something in it. If it's zero, the mailbox is empty. It's pretty easy to figure out. Makes the operating system stuff work very fast. Basically, what happens is that if I'm using mailbox, I've got a receiving task, and I pinned on a mailbox. And when something gets shoved in the mailbox, then I process it. TI's RTOS is different, as I keep coming back to. One of the big differences is the way that it handles mailboxes. So let me show you in this fashion. So I've got got mail here. This mail is for you. Okay? Right here, this is mailbox. Okay? Now, our mailbox, very small mailbox. It can hold exactly one item. Okay? So if you're waiting on the mail, right? I put something in the mailbox. Now the operating system, yeah, now you can take a look at it, right? And if I want to give you another piece of mail, I can certainly do that. I can take another piece of mail and I can put it in the mailbox. Hey, you've got mail. Okay. All right. Now, this is kind of the standard when an operating system handles a mailbox. Let's pretend for a moment that you're not home. Okay, so I come by and I got this mail for you. I put it in the mailbox. Okay, you're not at home, so you don't pick it up. I got another letter for you. It won't fit in the mailbox, right? You've only got a one-slot mailbox. So I have to wait till you get home. Now you're home. Go ahead, check your mail. You got mail. Oh, look, there's room in the mailbox. Here's another one right there. Okay, that's the way mailboxes work. Mailboxes have a finite size, and for virtually every other operating system other than the TI operating system, when you use a mailbox, it's going to have one slot in it. Okay, it can have one value at a time, which means that unlike, so a semaphore, if I pinned on a semaphore, obviously I wait, right? But think about a semaphore in terms of posting. Would there ever be a reason that that you might have to pause, give control back to the operating system if, as a task, you post to a semaphore? What do you think? Is there a reason that you couldn't just post it and go on? You guys can think of. Okay, but basically we're just setting up the flag. Hey, flag's there. Once that flag's set, if somebody comes in, the flag's already set, and I tell you to set it again, it's not going to get any more set if I set it. And it doesn't really do me any good to wait because, hey, it's set, right? Mailboxes are different because that next piece of mail is probably coming from someplace different or has a different value in it. And so in a mailbox, if you do a post and that mailbox is full, one of two things is going to happen depending on how you set up the call. One is that you could just receive an error, says mailbox full. And then you, as the poster, figure out, what am I going to do about that particular error? Or you can have it depend when you do a post and the mailbox is full. So in that case, if I post and the mailbox is full, I'm going to wait around until the mailbox has room for the message that I want to pass on. Now this is where TI's is a little different, because TI can set a mailbox depth. Okay, so you can set the number of messages that the mailbox can hold. In general, when you're using mailboxes, it's just going to be one message. But you could have a 30-slot mailbox where he could go off to the mall and not come back to check his mail, and the mail would never be full until he's at least 30 messages waiting for him. Okay? So that's kind of the concept that TI has. I'm going to give you a vocabulary here. It's called a queue. In other operating systems, that's not implemented as a mailbox, that's implemented as a queue. Now, the reason why TI chose to do it this way is because when they architected their system, I believe they looked at it and they said, hey, look, we've got to implement message queues. Message queues look like mailboxes. Let's just use the same mechanism. And by the way, part of the kernel is a queue handler, but it is not really RTOS aware in that the queue handler will just handle linked lists. You can put on, take off, do all your things. That's called queues in the kernel, and it's available to you as a library call if you want to make your own separate queues, but it's different than a mailbox because you can't depend on it and post to it. So again, a message queue is a little different, but in the TI RTOS, we don't make any change. Now, the trade-off, and you'll see when we start talking about creating a mailbox, is going to be in memory and performance. So the TI operating system, mailboxes are a little bit slower than in other operating systems because they have to make provisions for lots of different things that most mailboxes don't have. So if I'm writing something in FreeRTOS and I'm using a mailbox, it's a byte word, it's some atomic value, some atomic memory value in size, and we just read and write that value to the box. In the TI operating system, what we're going to be doing is we're creating this buffer that's going to hold information about where the first message is, where the last message is, how many messages there are, and has a copy of what it is that we're storing in the mailbox, which means that every time I do a storage, every time I put something in a mailbox, it's not one memory to memory transfer. It's, oh my gosh, I got to pick this thing up. I got to move it over here. And then when I pull something out of the mailbox, I got to move it out of here and move it over here someplace local. It involves some extra operations. So it takes a little bit of time than in other operating systems. Shouldn't affect your designs, but it's something that you ought to be aware of. And certainly something that when you start having performance issues, that you might want to think about globals and semaphores if you need to be really, really fast. So we're talking a little bit about the peculiarities. Let's see if there's anything that I haven't covered there. Nope, I gave you all that information. Okay, one thing that you should be aware, oh, you know what? I need to put that on mute. Somehow it is echoing me, or somebody's got their microphone on. Let's do manage participants. No, it says everybody's muted. Let's mute me too. unmute, and then we'll go down here to that's weird. Okay. Mute you. Okay, share screen. That screen. Share. All right, everybody can see that now, right? Okay. So let's get this, well, you're only missing the title. So let's talk about one example of how we might use, let's see, come on guys. There you go. Well, okay. Okay, so let's look at an example of how you might use a mailbox. So, as with all examples, it's kind of a lame example, but it's there to give you some idea of what's going on. So let's take a look at the overall structure of what I'm trying to do here. So I've set up my A to D converter to periodically convert on an interrupt basis, okay? So an A to D interrupt is going to occur on a regular basis, bang, 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 bang. I've set it up so that it's continually converting. And so my interrupt routine is going to read the A to D converter, and it's going to stuff that value into a mailbox, okay? Now I have this thing called display task, and what he's going to do is he's going to sit there and he's going to wait for a value to get stuffed in from the A to D converter, and he's just going to print it out on the serial port, okay? So you can see what's going to happen here. A to D value, it gets posted, 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 posted on a regular basis. And my display task is going to be pending. He's going to pend until he sees we got the post, and then we're pending here. Well, there's a value in there, so that pend does wait. Okay, post, pend, post, pend, post, pend. And each time we exit from that pin, we're actually going to write something to the LCD display. And so, in effect, what you're doing is that we're posting. This guy is waiting. He was waiting over here. He pended way over here. But as soon as that post happens, the pend exits, and he runs again. He writes to the display. He pins. The post happens. He pins again. So let's take a look at the code that does the pseudocode that does that. So there's my interrupt routine. All it's doing is reading the A to D value and posting in the mailbox. And the display task pins, comes down here, does a while loop. It pins until it gets a new value. It prints it out, goes back and pins again. What it does. Pretty simple. This is a little more complicated using it as a queue. So if we make this a larger mailbox, and we draw those as queues, right? Make this a larger mailbox with multiple things in it. We've got this serial output task. So I've got, that's okay. At least you're paying attention. Okay. So I've got these two tasks that are putting stuff, that want to print stuff to the serial output task. And they're each going to call this function called putS that uses putC to shove stuff on this queue. Serial out looks for a character and shoves it out the serial port. What happens is that I've got two different tasks, task 1 and task 2, that are calling putS. Red means that he's the active task. So he gets some stuff and he talks and puts stuff into this exit queue mailbox. And what happens is that the serial output task right here is going to periodically pull stuff, okay? But at some point, the serial output task is lower priority, and he's not going to be running. So this guy's going to put. Then this other task is going to put. All of that is sitting in this, is sitting in the mail queue buffer, and it gets pulled out by the serial output task later on, okay? You can see the different colors there about when they get pulled. So here, the code is basically the same. The difference is that we've changed the size of the buffer.
What was the trans buffer?
So trans buffer is, that is the transmission buffer. And where do I have that on here? Serial out task, yeah. Yeah, so the transmit buffer, that's actually the transmit buffer on the UART. And so it's showing that it can get filled up, and we have to wait here before we can put out more characters while it gets emptied out. Okay, mailbox functions. Well, it's TIR toss. There must be a params inet function, right? Now, it turns out there are actually two elements after you params inet that you must initialize. The defaults don't do you any good, okay? The first one is a buff in that parameter structure. It's basically a pointer to a buffer that you're going to allocate that stores all the mailbox information, okay? And then you have to indicate how big that buffer size is. So as it turns out, you can't just store, so let's say that we have a word in our mailbox, right? You can't just store your mailbox as 16 bits because there's other stuff that's associated with each mail entry, and that's in a structure that you'll never use, but you have to be aware of, called mailbox mbox element. That's a type def, and you have to store, for each element that you store, you have to store however big what you're storing is. So, you know, we're talking right now about a mailbox holding, say, an int value, but you could have a mailbox that held, I don't know, a structure that had 20, 30 bytes in it, right? Okay, so you've got to have, for mailbox entry, you got to have enough room for that structure or for that int, plus you have to have enough room for each element for that piece, okay, which is not important. You don't see what's in it. It's just important you save space for it. And you have to have that times the number of messages. So if I'm only making, so when I create my buffer, I have to make it this big, depending on how many messages I'm going to put in my mailbox, dependent on the size of my mailbox, and I have to have room for this overhead stuff. And that's the penalty you pay for doing this the way that TI does. It takes a lot more memory to create a mailbox in the TI operating system that does in other simpler operating systems. Advantage is you got one thing to do that you don't have to think about queues being something different. They're just bigger mailboxes, right? So you don't have to do a different calling sequence. Maybe it simplifies it some. So when you construct the mailbox, you have to give it a structure. You have to give it the message size. You have to give it that structure. And you can, this is optional if you make that a null. That's just a pointer back to a word-sized value that you can return the error code that gives you specific errors. So you'll see that. I don't know that I've covered that in other lectures. A lot of these kernel calls have this last parameter, EB, that we normally just make a null. But if you make it a pointer to a word-sized value, if there is an error code, if an error happens when you make that call, then you can go out and actually read that value and go searching through all the operating documentation to tell you what your mistake was. Okay, so in general, in real time, it's not real helpful because they don't have a super consistent way of identifying what those are. There's a huge list of these items. It's better in real time to simply say, hey, I got an error. Is this a touch screen? This is not a touch screen. Okay, what's happening over on y'all's Zooms? You're seeing the same thing? That is so weird. Okay. So what we're passing to the mailbox construct, this is the structure that you've created that holds all the mailbox stuff. Message size, that's the size of an individual element in the mailbox structure. So that doesn't go up in the actual, that's not buff size. Okay, so if I'm storing a 16-bit integer, message size would be 2. Okay, and if I only have one element in the mailbox, the size of my buffer would be 2, the number of bytes it takes for my message, plus the size of that structure, which we don't need to know, we just need to know that it's there. And that would be this buff size, different from message size. If you make these two values the same, pointers are going to get out of whack and there will be much weeping and gnashing of teeth. More importantly, there will be loose pointers, which always are difficult to debug. Params is the pointer to the structure that we created up here and initialized, and of course the error block. We get the handle, so we're not messing with the pointer to the structure all the time. We've got the handle that we're using when we get ready to pinned and post, which we're going to be using down here in our pinned and post functions. So pinned, we pass it the handle, we pass it a pointer. We don't pass value we want to put in the mailbox, we pass it a pointer to the value that we want to put in the mailbox. Okay, and then we give it a timeout because we're pending. We can wait forever. We can choose not to wait and just check the error code to see if there was an error when we pinned it, didn't work. Or we can set a timeout, okay? Just like you can with semaphores. And for posting, same kind of thing. We're passing the handle, we're passing a pointer to where we're going to store the message. So when you call this, when it returns from, or when you do the post, it's actually going to take whatever this was pointed to, put it into that message structure before it pops it up here. So again, this is not the value that you're posting. This is a pointer to the value that you're posting. And again, you can have a timeout. Any questions about mailboxes so far? Okay, so let's look at an example. So I'm defining my mailbox size to be 20, which in this case, that means that I'll have, it's basically, I'm initializing a queue that has 20 mailboxes in it. And, oh my God, I didn't test that code. That code is wrong. Okay, so can somebody tell me what I did wrong here? Place I spotted it was the declaration of the buffer. Then I looked down at how we're creating the buff size, initializing the mailbox parameters. Can anybody tell me what I did wrong? I didn't account for the overhead in the buffer. So this looks like what my intent was. Let's go back and try to figure out what my intent was for this example. See if I can see it down here. Okay, so it looks like I wanted to have single byte entries. Looks like I wanted to have 20 single byte entries, right? Okay, so if we go back up here and we look at that code right there, so mailbox inbox element is the overhead. So what we should have done, and what else? Yeah. Okay. So what we should have done, I'm just going to do that here for us. Let's fix it. So we're going to go up here and, oops, escape. Go back up here. What we're going to do is that we're going to do pound define buff size. And that is going to be equal to tx, size of mailbox, inbox. What was the spelling on that? Inbox elem. Plus 1, because that's the size of, well, we'll do this, plus size of care times tx mb size, and then we're going to put this as buff size, and we're going to have this as, so it turns out that is correct for the buffer size, but what is wrong is that that is size of care. Okay, so we will all right, let's go back to what we were doing. All right. Oops. Most common mistake, by the way. So I have now saved you from that trap. This is the most common mistake using PI mailbox stuff, is getting the buffer size wrong, getting one of those elements wrong. So let's go back, let's review. So this is the size that our buffer has to be. It's the size of this plus the size of whatever we're putting in the buffer times the number of mailboxes we're going to open up. Okay? We initialize that. We call the mailbox. We got to declare the buffer. We have to declare the params, the mailbox params structure, which this can be reused. I don't have, every mailbox that I create, I don't have to create a different one of these. I can create one and simply change the two elements in it. I have to declare a mailbox structure, and I have to have a handle, okay? Then to initialize it, I call the initializer. I point to the buffer, and I take the size, and then I take the, set up the buff size, tell how big the buffer is. And then we do the construct, and we have to pass to the construct how big the individual elements are. So when we get ready to use this, I want to post a character. I do a mailbox post, and I send the address of the character. And when I want to get an item out, I give it the address of where I want that to go. That makes sense to anybody? It's pretty easy to use. You'll be using mailboxes here shortly. So mailboxes, semaphores. 90% of the inter-task communication you're going to be doing in any real-time system. What I'm going to talk to you about now are events. We're doing okay, not finish events today. We'll give it a try. So you know what a binary semaphore is, right? You're playing with those. You've actually used a binary semaphore. Have you ever thought what would happen if you had a task that you wanted to pin on, but you wanted to say, okay, well, if this event happens or that event happens, okay, I want to pin on that or that. I don't know which is going to come first, so I kind of want to pin on both of them, right? That's something that's real easy to think about, the sorts of things that might get us into that. So let's say that I had a switch handling routine. I was waiting for a push button. You might want this task to pinned until any button got pushed, but it's important to know which button got pushed, right? So you don't want to have two different semaphores, because what happens if the one you're pending on is not the one that happened, but it's the one that you're going to do next? So that's what events are all about. And not every operating system, okay, what the heck is going on? This is going to drive me nuts. Okay, so let's go back to screen share. Share that screen. I think this is because it thinks that I think it's thinking that because we don't have the speaker on, that it's confused. Oh well. All right. So